Hey everyone, we're going to be looking at class 3.7. We're going to be using a simulation today. If you go to PhET and Gravity Force Lab Basics and just open up that simulation, we'll be referring to it a little bit today. So our goal is to describe how mass and distance affect the force of gravity between two objects, derive Newton's law of universal gravitation, and calculate the force of gravity. So Newton was pretty good, but he has limitations. He understood how the mass of objects and their distances from one another affected the gravitational attraction between them, but he couldn't really quantify the force of gravity. So we're going to repeat some of what he did. So please open up the simulation here, and I have it open in another tab. So first thing we're going to look at on this page is how does distance between objects' centers affect the force of gravity between them? All right, so let's check this out. It looks like the noise in the simulation is really annoying, so I'm going to turn my volume off. So it looks like as we get closer, are going to go farther apart. Notice how closer force goes up, farther force goes down. Oh, there's actually a button there to turn off the sound. So closer force goes up, farther force goes down. Notice how small the force is. Okay. Um, I don't think I can change these masses. Don't worry about what it is too much. Really just look for the relative sizes here. All right, so closer, force of gravity goes up, farther, force of gravity goes down. Now, what do you notice about the magnitude and direction of the forces acting on one another? So this is a really important idea. Notice that even though M2 is 4 times the mass of M1, they still always feel the same force as the other one. This is Newton's third law in action. So what do you notice about the magnitude? Equal magnitude, opposite direction. So just to reiterate things, as distance goes up, we call that r, by the way, we'll get to that later. As distance goes up, the force of gravity goes down. As the distance goes down, force of gravity goes up. So why would we call this an inverse relationship? Because as one goes up, the other goes down. So what happens if you double the distance between two objects? So let's see if we can do this. So I'm going to set the objects to be, let's put them 2 meters apart. So you have this ruler here. You could actually move it up to make sure that they're pretty accurate. So let's keep it easy. Let's put this guy at 0. Let's put this guy at 2. All right. You'll notice we have, let's do scientific notation. That should be a little easier to see. 6.67 times 10 to the negative 7 newtons. But let's double the distance now. Look what happened to the force. Now it's 1.67. So think about what just happened there. We went from 6.67 to 1.67. So if we have 1.67 over 6.67, that's actually equal to 1/4. So we have 1/4 the force of gravity. If I were to triple the distance, so instead of being 2 meters apart, if I'm now 6 meters apart, notice we have 7.2 times 10 to the negative 8th. What we can do there is, so that's going to be 7.2, or let me just be careful here of how I do this, 7.42 rather, times 10 to the negative 8th, over, I think our original one was 6.67 times 10 to the negative 7th. You're going to get 1/9 there. So throw that in your calculator, you get 1/9 the force of gravity. All right, so what we end up finding here is that This isn't just the regular inverse relationship, this is an inverse square relationship. So FG, this symbol here means is proportional to. This shows up all the time in physics textbooks. Is proportional. Let me actually give myself some more space there. Is proportional to. That's what that symbol means. 1 over r squared. We use the symbol r. Okay, r is the distance between objects' centers. Now you might be asking yourself, why is it r? Why isn't it d or something like that? You might see d somewhere, but I'm guessing here the origin for r is because like the distance between, let's say, the Earth and the Sun is the radius of the Earth's orbit. So I think that's where that term may have originated from. But r is simply the distance, is not half the distance between their centers. Okay, and please make sure you're actually putting these numbers into your calculator and actually seeing those relationships. Now, they won't come out to be exactly 1/4 and 1/9, but they'll be pretty close. By the way, I think this simulation, this link actually brings you to a slightly different simulation where the numbers will actually work out probably better. Gravity Force Lab Basics. So that's probably my problem here. I'm not using the basics version. If you go to this one, it's not a huge difference. The numbers are just going to be more reasonable. So this one has ridiculously large masses. Again, this sounds annoying. So this one is actually a little bit better. See how it just gives you the distance? So you can see the same thing. You have 2 kilometers to 4 kilometers. You'll get 1/4 the force. And if you go from 2 kilometers to 6 kilometers, you'll get 1/9 the force. All right, so just make sure you throw those in your calculator so you can see that. All right, we'll use the simulation now. So now we'll look at how mass affects it. So let's play with the mass a little bit. If the mass goes up, we can see the force go up. If the mass goes down, we can see the force goes down. And that's for both of them. So as mass goes up, force of gravity goes up. As mass goes down, force of gravity goes down. So let's set them to be 1 billion kilograms and 4 kilometers apart. So don't change the distance for this part. So how does increasing the mass affect the force of gravity? The force of gravity is going to go up. So m goes up, force of gravity goes up, m goes down, force of gravity goes down. We already said that. So why do we call this a direct relationship? Well, as one goes up, the other goes up. So how does Fg change if you double one of the masses? Let's double this one here. So we have 4.2, 8.3. So it doubles. Now, the reason it's not perfectly doubling is because there's probably some more significant digits there that we can't see, like maybe it's 4.15 or 4.16, and we can't really see it. So if the mass doubles, Fg will double. So if we double the mass, we double Fg. Well, what if you double both masses? Well, if I double both masses, I go from 4.2 to 16.7, so I quadruple it. So if I double m, and it's probably not the best way to write this. So if I double one mass, I'm just going to say what happens. Double Fg. If I double both masses, I quadruple Fg. Actually, I'm going to write 2x. Kind of like that. If I double both, I quadruple Fg. So this is a linear relationship. As one goes up, the other one goes up right with it. So Fg, Newton said, was proportional to m1 times m2. If you're not changing one, then it's proportional to just, if you're not changing m2, then if you double m1, you double Fg. But if you're changing both of them, it's proportional to both of them. All right. So Newton came up with this universal law of gravitation. It looked something like this. Fg equals g m1 m2 over r squared. It looks something like that on your reference table. Just find it and make sure you're familiar with it. But it looks something like this on your reference table, where g is a constant. M1 is going to be the mass of object 1, M2 is going to be the mass of object 2, and r is the distance between them. Those are in kilograms. This is distance between objects' centers. That part's really important. For example, if you were doing this equation for like the force of gravity between you and the Earth, r is not the distance from you to the ground. R is the distance from your center of mass, about your belly button, all the way to the center of the Earth. So Newton knew these relationships, but he could not calculate g. And it wasn't until this guy Cavendish in maybe the 1700s or so did an experiment where he could calculate g. His experiment is absolutely fascinating, the fact that it works. If you check out this video here, someone actually did it in a physics classroom. Real easy setup. Now, quantifying it's a little more challenging, but at least seeing the effects is pretty neat. So what is the value for g? G is equal to 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Don't worry too much about the units. Just know it's a really small number because the force of gravity is really small. So what would the force of gravity be between two students? Well, let's say a student has a mass of about 70 kilograms. That's 154 pounds. So we would do Fg equals 6.67 times 10 to the negative 11. Let's say they're each 70 pounds, so 70. And let's say it's two students sitting in desks next to each other. So they're about, actually, let's do 2 meters apart just so it's not 1. So 2 squared. So let's do, let me get my calculator out. 6.67. I'm doing this on my phone, so I can't really do it that well. The scientific notation times 70 times 70. So I'm getting 8.17 times 10 to the negative 8th newtons. Okay. Now, how big is that number? That's really small. That's 0.1, 2, 3, 4, 5, 6, 7. That's basically nothing. Okay, if you had a penny sitting on your hand, that would be applying more force to your hand than the force of gravity between you and a student that's about 6 feet away from you. So the force of gravity is really weak. That's why we don't notice it between two objects on Earth, but you notice it between you and the Earth. And think about how massive the Earth is, and you can overcome the force of gravity to some extent by jumping off the ground. So it's a pretty weak force. So these two questions here are pretty interesting. These are factor of change questions. That's the method I would use here. So we have 2 cups of water, both of mass m, that are a distance d apart. The force between them is F0. Now we're going to take some water from one and pour it in the other, same distance apart. So we have to find the force of gravity between them. A lot of people would assume that force is the same, but it's actually not the same, and we'll see why. So let's write out our force of gravity equation. Fg, well, actually, I'm just going to write F0. F0 equals G m, let's write m1, m2 over r squared. Now, how do we use factor of change here to find the new f naught prime? Replace each factor with what you're changing it by from figure 1 to figure 2. So for example, let's even include g. I like to include g here. Is g changing? No, it's not going to change. G is never going to change. So replace it with a 1. G is not equal to 1. Okay, it is not equal to 1. I'm just saying it's not changing. So if m1 is the mass on the left, how is it changing? How many times bigger or smaller is it? It's 1.5 times bigger. How about m2? It's half as big. And d, that's not changing, so I'm just going to write 1 squared. Don't forget to put that square there, even though it doesn't really matter for this one. You should still put it there. What you get here is 0.5, or 0.75 rather. Now, 0.75, what is that? It means it's 0.75 of the original force. So that would be choice A here. So I want you to try this here. Same deal. Go through the same method. Okay. How is M1 changing? That's the satellite. How's M2 changing? The planet. And how's the distance changing between their centers? All right. Try this one out. See how you do. I think the answer for this one is also, I'll just give you the answer. I believe it's 3/4. Just trying to do it in my head really quickly. Yeah, this one comes out to be 3/4. So just make sure you show the work for that and submit it. All right, so now you have Newton's universal law of gravitation. And these are actually two from your AP Classroom questions, so you can get those going as well.